Hi, my name is Manish Gupta, and in this video, I'm going to talk about Zcode++, which is a pre-trained language model for abstractive summarization. So recall that abstractive summarization is a complex task where the input is a document and you need to write a summary in your own words without copy-pasting paragraphs or sentences from the original document. Now, why is Zcode++ important? Because it actually performs really well on these abstractive summarization tasks. As the paper claims, out of 13 different summarization tasks, Zcode++ was able to win on 9 of those tasks across 5 different languages. Some of those are shown here. So these are standard English summarization tasks, but there will be results about multilinguality and so on across other languages in the next few slides. So across these several data sets, XSum, CNN, Daily Mail, these are all popular English summarization data sets. So as you see, Zcode++ is the last column here, and then the previous column is Pegasus Large, which is again another popular abstractive summarization model. So as you see, on average, Zcode++ performs better than Pegasus Large, and it is somewhat sort of comparable or slightly better compared to the best model out there for each of those 7 different data sets. So for example, if you look at SAMSum, this particular data set, Zcode++ is like 30.3 compared to prior state of the art of 29.8 versus 26.3. Okay. So these numbers are actually F-measure Rouge2 values. So, Rouge is a popular family of metrics for measuring summarization, and Rouge2 specifically measures bigram overlap between the ground truth and the generated summary. Okay. So on standard English summarization tasks, Zcode++ is actually better compared to the PaLM 540 billion parameter model, especially on XSum dataset. And PaLM 540 billion parameter model is like 600x larger compared to the Zcode++ 710 million parameter model. So it's better than a much larger model. Okay. Similarly, the similarly, Zcode++ is actually also better compared to the 200x larger GPT-3 175 billion parameter model, especially on the SAMSum dataset. Okay. So Zcode++ is sort of better compared to much larger models, giving you better accuracy for abstractive summarization. Okay. So this model, the first version was out in, or rather was created in or trained in 2022, and it sort of topped the XSum dashboard at that time. So essentially, compared to the UL2 20 billion parameter model or the T5 11 billion parameter model and the Pegasus large model, it basically was the winner. Okay. Now, it also performs well on this long document summarization task. So these are not standard English data set. They're like long document summarization data sets, very long documents as input. Okay. And as you can observe, there are comparisons done with long T5 X large, extra large, long T5 large, Pegasus large, and then any other prior state of the art, right? And as you observe, in most of these cases, Zcode++ is giving you better results. The results are not, highly better. I mean, margin of improvement is not too much, but as you observe, they are still better than the prior state of the art in most of the cases. Yeah. Now, they also did average side-by-side human preference, asking people, hey, given this summary and given the Zcode++ generated summary, which one do you prefer? And as you observe, they compared across several models, UL2, BART large, Pegasus large, T5, 11 billion, and so on, and compared across different metrics, conciseness, fluency, if the model is creating any hallucinations and so on, informativeness and so on. Overall, across all models and across all metrics, they observed that Zcode++ is slightly preferred more compared to other competitor models. So how is Zcode++ trained? Well, Zcode++ is a standard encoder-decoder architecture. In fact, the Zcode++ large is the most popular checkpoint, which is like 24-layer encoder and 24-layer decoder. It has a dimension of 1024, 16 attention heads, and a 128K sized vocabulary, specifically for English. So this is for English, right? So for the multilingual version of Zcode++ large, that's basically trained with the MC4 data, which is the same data, by the way, that was used for training MT5 model with a vocabulary of 250K. Now, if it is standard encoder-decoder model, how does the architecture, how does the training differ, right? So architecture does not differ much, the training differs, okay? So the training differs in 3 interesting ways. It has a 2-phase pre-training, and I'll talk about that in detail. It has DBERTA-style disentangled attention, and the third one is it has a fusion-in-encoder for sequence encoding for long sequences, right? So specifically, fusion-in-encoder is basically a hierarchical way of doing encoding. Okay. So let's talk about them one by one. So what is two-phase pre-training? Well, two-phase pre-training has two different stages or phases. So the first phase is Electra style phase. So Electra is a popular pre-trained model by itself, which basically uses these two different losses, RTD and CSP. Okay. So rather than using just the MLM loss, it basically also uses RTD and CSP along with it. Okay. So what is RTD? RTD is replace token detection, and CSP is corrupted span detection. Okay, so let me explain this one by one. So essentially, so different colors basically indicate different transformer, shared weights or not. Okay, so essentially this encoder and this encoder here will share weights. Okay, so what does RTD do? So essentially, you have a transformer generator model here. You call it generator. It's like a transformer thing, right? So basically, just several layers of transformers in that. Okay. It's essentially a transformer encoder from an architecture perspective. Okay. So you take input text. This is an input document. You mask out around 15% of those tokens represented as M. Okay. And the original token was X3, X6. Those were masked out, right? Generator's idea, the goal is to be able to do MLM, so predict these X3 and X6 appropriately, right? Correctly. Now, the generator can make mistakes. It can actually generate X9. But the idea is that first you try to minimize this MLM loss. That's the MLM loss. The second, you then have an encoder on top of this generator, which, but by the way, both of them are transformer encoders. They just don't share their weights and embeddings. Okay. So, but you basically take the input that is generated by the generator, this one, and then try to predict if for each of those tokens, was it correct or wrong? Was it original or replaced? Original or replaced? And that's why it's called replaced token detection, RTD. Okay. So you have two losses already, one MLM and the other is RTD. And then after the output is generated by the encoder, you essentially give that to the decoder. So then it is a standard encoder-decoder kind of a framework where the decoder tries to do corrupted span prediction. So, if you have a particular span that was input, so, you masked out a span, so X3, X4, X5, you input to the encoder, and then you basically ask the decoder so as to be able to correctly identify this X3, X4, X5. I mean, in a typical decoder kind of a setup where you basically do like shifted outputs are passed as inputs to the decoder and so on, along with, of course, cross attention from encoder to decoder. Okay. So that's that. So essentially, the first phase in the two-phase pre-training involves three different losses: MLM, RTD, and CSP, the corrupted span prediction. Okay. So you try to minimize the three together with some lambda coefficients. In stage two, it's basically continual pre-training. So you continuously pre-train this stage one model on collection of summarization data sets with the document summary pairs. So document goes as part of the input and you try to predict the summary and on the decoder's output. Okay. So they try to do this so as to basically make the model ready for fine-tuning on specific summarization data sets. But at pre-train time, they actually pre-train using these four summarization data sets: media sum, multi-news, newsroom, and WikiHow. So these are a combination of data sets across domains like news and interviews and Wikipedia and so on. Okay, so that's that. Now, the second thing, the way Zcode++ differs from the standard encoder-decoder is in DBERTA style disentangled attention. So remember the self-attention layers? Well, the input to the self-attention is essentially a combination of token encoding and the position encoding, token position. But in DBERTA, essentially, they propose this disentangled attention where you replace your self-attention layers with these disentangled attention layers. And in disentangled attention layers, the idea is that you have a different attention, or rather for each token, you keep the content and the position encoding separately. So therefore, the attention is computed content versus content, content versus position, position versus content, and position versus position. So you keep all of those attentions separately and do those self-attention computations. Now, more details about DBERTA are in the DBERTA video. So I recorded a DBERTA video earlier. They basically just make use of the disentangled attention sublayer from DBERTA model here in this particular framework, in this particular model also. Okay. The third important difference is in fusion-in-encoder for hierarchical sequence encoding. So remember, in summarization, the input document could be very large, and your max sequence length for the input, the context length, is limited. So to solve that problem, what they do is to split the input sequence into small chunks, and they apply self-attention on each chunk locally. So as you see here, so you divide the input sequence into chunks, you apply self-attention, local encoding, local self-attention within that chunk only. And then once you are done with that, you basically take the last layer outputs from each of those chunks, you pool them and essentially give them as input to global encoding layers, and then apply the typical encoder, which sort of then, and then apply the typical encoder, the global encoding layers, which sort of do the attention on those chunks only, Okay. So that's that. So essentially, in some ways, by dividing the input into chunks, you're essentially trying to, handle the long sequence input by splitting it into parts and then doing attention locally and then combining it to finally do a global attention across chunks. Okay. So that's that. So overall, Zcode++ was pre-trained using 160 GB data, 128 800s for 20 days. Okay. So lastly, let me talk about how does Zcode++ perform in multilingual and zero-shot or few-shot settings. So multilingual setting, essentially, they try to do cross-lingual summarization and multilingual summarization. So cross-lingual, basically summarization from Russian, Vietnamese, Spanish, and Turkish to English, right? And multilingual summarization using the MLSum dataset. Okay, so Wikilunga and MLSum datasets, popular datasets in multilingual and cross-lingual summarization. Okay. So cross-lingual summarization basically means that your input document is going to be Russian, but the summary is in English. That's what cross-lingual summarization means. Okay. So if you look at the comparisons, Zcode++ does better compared to MT5 extra large and MT5 large models. You basically see these numbers are better in that senses, both for cross-lingual and multilingual summarization. Now, of course, Zcode++ does not beat PaLM models. PaLM model is better in terms of multilingual summarization in some cases, at least. So in multilingual summarization, in fact, Zcode++ is better than PaLM. But in cross-lingual summarization, sometimes, PaLM actually gives you better results. Okay. So that's that. But then remember, PaLM is actually much larger, 540 billion parameter compared to just 710 million parameter. So for multilingual, yes, Zcode++ is good, but for cross-lingual, looks like PaLM is better. Okay. So in zero-shot and few-shot settings, well, to basically evaluate how good Zcode++ is in these settings, they basically experiment with the 3 data sets, XSum, CNN Daily Mail, and SAMSum, right? And compare with 4 different models. And in these 4 different settings, so these 4 settings are basically how many examples from these data sets did you use to fine-tune the checkpoint, right? So 0 basically means zero shot, and then 10, 100, 1,000 just mean different levels of few shot. Okay. So what can be observed, and then they compare with T5 large and Pegasus large. Well, there is a Zcode large variant that they also compare with. This is basically the variant obtained using only the first stage of pre-training. Okay. So the one with the dagger essentially is the variant where they do not do a summarization-based second stage of pre-training. Okay. And what you observe is that on average in zero-shot and few-shot settings, also Zcode Zcode++ large is much better compared to T5 or Pegasus large. Right? Of course, this second phase of pre-training matters. As you can see, this guy is actually pretty poor, right? But then Zcode++ large is much better. So the one with the dagger is actually pretty poor, basically saying that the summarization-based pre-training second phase is actually super important rather than just doing the first phase of pre-training. Okay, so in short, Zcode++ is a pre-trained language model for abstractive text summarization. It is based on a transformer encoder-decoder framework. It involves a 2-phase pre-training process, disentangled attention from DiBerta. So it has borrowed interesting concepts from several models. So this 2-phase basically involves RTD and CSP, borrowed from Electra, and in some ways Spanbert, because Spanbert was probably the first model which involved span-based masking, right? The disentangled attention mechanism is sort of taken from DiBerta, and then fusion-in-encoder is basically sort of common in some ways for encoding long sequence inputs. It established state-of-the-art results on text summarization, 9 out of 13 text summarization tasks across 5 different languages. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.